Thanks, Keelan, and thanks, Peter, as well, for inviting me and also helping me to get organized and everything. A little bit of background about myself. My name's Nick Grattan, and I work for a company called Dassault Systèmes, which is probably one of the larger software companies you've never heard of. Anyone heard of Dassault Systèmes before? Okay, one person. We're 16,000 people, so we're a reasonably large company. And we do software for 3D design simulation. And so our software is used for designing Boeing jets, Airbus, Toyota cars, Jaguar, and we also do simulation as well of most everything. So we're simulating Singapore at the moment and on a whole lot. So very, very interesting company, and I do the documents, which doesn't sound quite as exciting or interesting, but that's my background, that's where we come from. Some of you, if you've been in the industry for a while, would have heard of a company called Cumus. And in fact, that's where I started out life, and we were bought out by Dassault. So we work in the life science industry, helping people to manage the research, clinical trials, and the release of software for pharmaceutical and life science companies. So that's my day job. I'm an architect there, and I look after documents and document management and text management. In the evenings, I'm also doing a PhD. Anyone here from the Insight Center? Okay, have you ever seen me? No, because while I'm doing the job during the night. Okay, I'll catch up with you anyway. So I'm a part-time PhD student there, and my research is on text analytics and natural language processing, and it relates to the work I do during the day. So I'm looking at how text evolves and the relationships between text as it's moved from document to document. Because in the world we work in, which is pharmaceutical companies, everything is very highly regulated. So when a document is changed, we need to know how that document was changed, who changed it, where did the change come from. So if there's a mistake in a particular piece of text, we have a chain of custody all the way back to where that text originated from. So that's what I do during the evenings, and I think I'm halfway through now, so it's going well. So the topic for tonight, the important thing is I'm going to do an introduction, okay? Because for many of you it would be a new topic, it would be something you won't have done before. So I want to do this as an introduction, and I want to cover really quite a broad range of different topics which are to do with text analytics and natural language processing. So this is about taking documents and text, which comes from any particular sources, and analyzing it and trying to get information out of it. And fundamentally, we can treat text in two different ways. One is we can just treat it as basically a set of terms, and then assign to those terms numbers, and then just do numerical analysis on the text. And there we can elicit out of that text information, but we don't really understand what that text is about. We don't have a semantic understanding of it. And many, many years ago, that sort of approach of text analytics was summed up by this guy, J.R. Firth, who said, "You shall know a word by the company it keeps." And I love that, because that really, really tells us about text analytics. Now, one or two of you have probably used Google before. I can assume you have. And you will know that over the years, Google, the search engine, has improved step by step. And it's got to the point now where it obviously corrects your spelling, but it also knows about the relatedness of words. It's starting to get an understanding of the semantics, the meaning of the words which you're typing in. And that's really what this guy was about. He was a linguist, and he was saying that if you just take a word by itself, it's just a word. But if you actually look at the context in which that word is used, you then start to get a meaning. You start to get an understanding of how that word is being used, and some of the understanding of the meaning of the text which you're looking at. And I just love that phrase, and I always keep that in mind. So what we're going to look at today, we're going to do introduction to text analytics. we're going to look at an overview of some of the common techniques I've been using, and I think they're useful for both research and also for people working in companies and in the commercial world. We're going to look at what I call traditional frequentist text analysis. And this is where we count things. And I borrowed that phrase, frequentist. Any statisticians amongst you? Okay, you would have come across this problem or this argument between the frequentists and the Bayesian people. I think I'm right on that. And the frequentist view in statistics is you count things and you look at the data, whereas with Bayesian you look at the probabilities. And there is that, to an extent, that sort of division within natural language processing as well. And we're going to look there at some very, very simple techniques which allow us to start to analyze text and documents and the words that they contain. We're going to look at bag of words, and we're going to look at how we can create vector space models. I'll talk more about those in a moment. And these are high dimensional, very low density spaces that we can create into which we can inject our documents and then start to compare them. And that allows us to do things which are quite interesting, which is we can measure document and text similarity. How similar are these pieces of text together? And we can do clustering as well, which gives us a visual representation of the similarity between those documents. And after the break, there's a hands-on exercise that will take you through taking some documents and show you the code which we can use to extract out the text and then make meaning from that text, and also to be able to display a representation of the similarity between those documents. But that's the counting bit. That's a word is just a symbol, and we use a program to manage and to analyze those symbols. And they don't have to be words, they could be anything you like. It's just the way we analyze them. We'll then go on to look at something called word embeddings, which I think is a very, very interesting technique, which has evolved probably over the last 3 or 4, maybe 5 years. It's a new technique. And what this does is it allows us to analyze text and rather magically work out the semantic relatedness of words. So whereas the first technique says that a word like king and queen have no relationship, they're just words. With word embeddings, what we can do is we can analyze a piece of text to work out that there is a semantic relatedness of those words. And how do we do that? Well, we look at the sentences those words are used in. And if we can actually say that the word king and the word queen are used in similar types of sentences, then we can actually extract from that an understanding that the words are actually related, and they have a semantic relatedness. And I think it's a bit of alchemy, I think it's a bit of magic, because it's totally unsupervised training, which is very, very impressive. So we're going to look at that, and the second exercise is actually creating word embeddings with word2vec, some source code to do that. And for those of you who have attended the first 2 meetings, where you learned neural networks, using TensorFlow, then that's what we're going to be using. We're going to use a neural network to do that. So that's quite interesting. So that's our agenda for today. So, some definitions. I've separated out here the natural language processing, the NLP, from text analytics, which is also called text mining as well. So, natural language processing is really sort of the area of AI which is concerned with the interactions between computers and the human natural language. And the important point here is it's about trying to understand language. Okay. Then a broader topic, which is actually much more accessible, is much more easy to get into, is the whole area of text analytics, also called text mining, which is given a very large set of data, can we elicit information from that? And there you're into the territories of search engines, of document similarity, of extracting documents which are similar, etc. So that's about information discovery. And of course, text analytics is really a superset which can contain natural language processing techniques which can be used within text analytics. And when you look at how Google is now working, you see that it's more than just text retrieval, text analysis. There is more natural language processing in there, understanding the words that you're looking for, and question answering, really. So what are the areas that natural language processing can be used for? Well, speech recognition falls into that area. Part of speech tagging, that's where you take a sentence and you work out what the nouns are, the verbs, the adjectives, etc. Disambiguation, this is a really difficult area. I'll show you an example of that in a moment. That's trying to work out what a sentence actually means, because there can be multiple meanings for a particular sentence. Named entity recognition, can I find names and product names, etc. from text? There's a whole bunch of areas around that. There's also, I didn't put it on this list actually, but there's also obviously translation as well, language translation. Did you see in the press that Microsoft now claim that their Chinese to English translator is as good as humans? That was announced today, which is getting frightening. And they're also claiming they can do real-time translation from a natural Chinese speaker into English in real time. So it's a big area. Okay, so let's start off with our text retrieval, our text analytics. So you've got this bunch of text out there, and it may be in a Word document, it may just be in plain text, it may be in HTML, it may be text exists everywhere. Okay? So how are we going to analyze it? Well, we're going to assume, let's assume that our text is in HTML or XML. Okay, and we're all Python guys, aren't we? Yeah, of course we are. How are we going to get that text out of there? Well, we use Beautiful Soup. And I just love that. That is the most exciting, most wonderful name for a module in Python, Beautiful Soup. And what it allows us to do is to give it a piece of HTML. It doesn't need to be well formed. And what it will do is it will actually work out the structure of it and give us a tree, a bit like a DOM, and within that will be the text. So we could use something like Beautiful Soup from taking a bunch of HTML documents, and then what we can do is we can then extract the text from it. So we get this large piece of text. It might be hundreds, it might be tens of thousands, it might be millions of words, just as this long string. We need to then take the next step of analyzing it. And what we typically do there is we then tokenize it. And tokenizing is breaking it into separate words. That sounds like a trivial task, but it's not. When you look at text, the way it's actually formed, particularly when you've got punctuation in there, particularly when you've got hyphenated words, for example, that process actually becomes quite difficult. And the other thing is as well, we tend to think of tokenization as an English or a European language issue or problem. We think of it in terms of the languages that we know. But then you've also got to consider around the world, there are lots and lots of languages which have very different constructs, very different ways of representing words, meanings, concepts, etc. So tokenization is actually one of the big problems. Forgive me, I am going to talk mainly about the English language here, but a lot of the principles apply to I say foreign languages, but other languages as well. The next thing we often do is remove the stop words. It's a strange word, this, stop words. What does that mean? Well, in a language you find that there are common words. Okay, these are words which are the, and, la and le. That's my French done for tonight, so we've done that. So we can remove those words because in some situations they give us very little additional information. Other types of research, they are important, but we can remove the stop words. The other thing which we sometimes do is stemming. And if you look at words, they actually have a base form called the stem, and then they have variations based upon either prefixes or suffixes, which change the meaning of the words, but it's still fundamentally the same word. So sometimes we will do stemming, fishing, fished, and fisher. We would stem back to fish. So when we're analyzing it, we would actually bring that word down, compress it down to a single meaning. There's a very, very good package available for Python for doing that called NLTK. And in fact, in the exercises this evening, we'll be using that. And as I say in the last point, sometimes we use those techniques, sometimes we don't. So what we end up with is now a stream of tokens. terms. Okay? So we now have our text broken into what are recognizable words. Sometimes you might go further. You might actually decide you're going to break it down to sentences, or you might break it down to paragraphs as being the unit at which you do your analysis. Depends upon what you're trying to achieve. So what are some of the fundamental ways in which we can analyze the stream of text? Well, the simplest way is what's called the bag of words. And what you do is you take all of these words from a document, and then you say, what is the set of words that I have? I don't care how often those words appear. I just want to know the set of words. And that's called a bag of words. It's just purely a set of the terms which you have in your document or in your corpus. And then if I've got two documents, I've got two documents here, doc1 and doc2. What I can actually then do is I can use a very, very simple distance measure or similarity measure, it can be used either way, called the Jacquard similarity. And I've given the formula here for it. It's basically the length of the union of the intersection divided by the union of the length of the two sets. And that gives us a value between 0 and 1, which gives us the relatedness between the two documents. It's extremely fast and simple to calculate, and it gives extremely good results. Okay? How similar are these documents? How related are these documents? We can go further, and we can then start to do use what are called term frequencies. And a term frequency takes another step forward from the bag of words. And what it does is it says, okay, I know the word exists in this document, but how many times does it exist? Okay, 3, 4, 5, 6, 7. And that gives us additional information that we can get out of this document. And so now we actually then create what's called a vector space model. And with a vector space model, we give a dimension to each of the terms that we have in our corpus. Okay? So in my corpus, I'm not very good at drawing more in 2 dimensions. Okay? So I've only got 2 words. I've got cat and mouse. Okay? And what I can do is I can look at these 2 documents, and I can plot these documents into this 2-dimensional space defined by these 2 words, and that gives me a relative position of these 2 documents. Yeah? Now, how many terms would I have in a typical corpus? I might have 10,000, I might have 20,000, I might have 50,000 different terms. So how big is my dimensionality of this space? Well, it would be 100, it would be 50,000, 10,000, or however many dimensions. And you can imagine that when I plot these documents or these pieces of text into that space, it's a very, very low dimensional space. Okay? And if you think about it, a lot of the term frequencies would be 0. So you end up with a lot of these objects, these documents, etc., at the periphery, and you end up with dimensionality problems, the curse of dimensions, and those types of things. But it does actually give us a useful representation of the documents in this new space. So once we've mapped them into that space, if I want to then start to find out how similar those documents are, I can just use a distance measure. Okay? And I've put 2 different distance measures here. Euclidean distance is just the linear distance between these 2 points, reasonably easy to calculate. And there's also the cosine distance as well, which is a different way of measuring the distance. These actually have different characteristics, and there are probably 428 different distance measures you could use if you chose to. All have slightly different characteristics and give you slightly different results. But using this, for example, Euclidean distance between 2 documents mapped into this very large dimensional space gives me a distance between them. Documents which contain similar words, similar numbers of words, mapped closely. Those which are very distant, map more distantly. There is, we're getting slightly more complex here. It's not too much more complex, but term frequencies suffer from problems to do with the frequency of words not only within the document but within the corpus as well. And what you actually end up finding is that the documents which occur very frequently in your corpus across your documents end up with a higher weight than you really want them to, because they don't end up being discriminatory, because they have similar frequencies in lots and lots of documents, and they just end up as noise. And so therefore in a lot of text retrieval and search engines, they actually use the term frequency inverse document frequency measure. And what this actually does is it adds a new term, not just a term frequency, but it also has an inverse document frequency. So what's the frequency of a word across the whole corpus? And this measure here then reduces the importance of documents which occur very frequently, but occur very frequently across the whole corpus. And so this is, you'll see this very, very commonly used, the TF-IDF, and particularly in document retrieval systems or text retrieval systems. So, we've taken our documents, we've tokenized them, we stemmed them, we've removed our stop words, we then injected them into this high dimensional space. We've worked out how to actually look at the distance between these documents. And so what we can then do is we can create a similarity matrix. So what is the similarity between a document and all the other documents? Okay. So we have a distance measure, so we can just do that. So for each document, we calculate the distance between them, and we end up with this distance matrix. And once we have this distance matrix, we can then start to represent those documents in a way in which we can actually understand. I don't know about you, can anyone project in their mind 30,000 dimensions? No, I can't. So let's bring it down. Well, once we've got this square matrix here, two very commonly used techniques are k-means clustering, which is just a clustering mechanism which allows us to visually represent clusters. I won't go into k-means, but it's commonly used. You'll see it used throughout the whole of text or analytics. The one thing about k-means is that you actually need to know how many clusters there are before you actually cluster. But there are ways of actually, predicting the number of clusters or estimating the number of clusters. But there are also techniques which allow you to not have to specify the number of clusters. The other one which we use very frequently is hierarchical clustering. And this allows us to produce dendrograms. Okay? And I love dendrograms because my first degree was in zoology. And I'll let you into a secret, it was a couple of years ago. And we did dendrograms. My first degree was in zoology, and we did numerical taxonomy. And you can imagine that for animals, you use these dendrograms for representing the phylogenetic similarity between animals, between different species. Well, here we're using it for documents. So for me, it's a lovely circle which I've gone around. But this actually visualizes very, very carefully. I also said, remember I said that the problem with k-means is that you've got to work out how many clusters there are? Yeah? Well, can you see from a dendrogram, you can estimate how many clusters there are. Because if I take, for example, the distance at level 100 here, can you see it tells me there's 2 clusters? If I go further down here, I might see that there's 4 clusters. And so you can use it as a way of estimating, and in fact you can do that numerically, not just visually as well. So can you see now how we've gone from just pure text, some HTML documents, we've gone through that whole process of the tokenization, distance matrix, and now we can visually represent the similarity and distance between documents or text or wherever that text comes from. One of the exercises we'll be doing exactly that against 13 or so documents from W3C, some of their standards. And it's quite interesting because you can then look at the relatedness between standards in W3. You're familiar with W3C. They're the people who do all the standardization of HTML and XML and all that type of thing. You can look at the specifications, and you can actually look at the similarity between the specifications and get some idea of the fact that the XML-related ones are obviously closer than the ones which are more to do with RDF or some of the other technologies they deal with. Any of you work with DNA? Any of you bioinformatics people? Okay. With bioinformatics, you know, DNA has the base sequences and the coding for amino acids, and there's a lot of work done in terms of looking at sequences and comparing DNA sequences with other sequences to see how similar they are. And what was really interesting, certainly from my standpoint, coming from a zoological background, is that those techniques were well established in the technology called bioinformatics, which is looking for generating phylogenetic, the relationship between species based upon their DNA sequences. And in fact, they use exactly the same techniques as we use for text, which is fascinating, and I really like that bit. My daughter is doing biochem in UCC, she's 4th year up there, and she said, I'm doing bioinformatics. Can you help me, Dad? And I said, yeah, sure. So we went through the bioinformatics. I helped her with the algorithms, that type of thing. She said, you learnt that in college, did you? Referring to my first degree. I said, no, because bioinformatics hadn't been invented then, which was a bit embarrassing, but there we go. I'm rambling. Where are we getting to? Well, there is this technique called, or this measure called edit distance, which given 2 pieces of DNA, okay, how many base sequence changes are there to go from sample A to sample B? And if you assume that each of those base changes is a mutation, okay, you can, and you know how often mutations happen, you can actually not only work out the similarity between species, but you can also determine at which point they, for example, became 2 different species. Okay, it's a lot of work done on. And there's an edit distance algorithm called Levenshtein edit distance. There's some related ones as well, which I won't go into in a moment, but there's a family of these algorithms. And what they allow you to do is I've just given 2 words here, execution and intention. What it allows you to do is to work out how many changes you need to make to go from one word to another, or in the DNA world, from one DNA sequence to another sequence. So you can say it's one insert, it's one delete, or it's a substitution followed by an insert. And the technique used here is the dynamic programming technique. Have they ever come across dynamic programming before? Okay. Some of you will have. It was developed in the 1960s, I think. And it's a technique whereby you create these matrices here, and what you do is, using algorithm, I won't go into the details of it, but basically you can map out all of the different possible ways in which you can get from this word to this word. And so you can come up with lots of different ways in which it can work. It was called dynamic programming because of a very technical reason, which you in research will understand. Money was short for research grants, and the guy who came up with dynamic programming wanted to make it sound really sexy so he could attract some research grants. So dynamic programming was what he came up with, and it's stuck there. So what we can do is we can actually take not only words here, but you can actually do this for whole documents. So you're given 2 documents, and here you're starting to talk about matrices which are quite large. What you can do is you can say, give me the edit distance, how different are these 2 documents, but also estimate how document A was edited to provide me with document B. And out of this, by tracking back, you see these little arrows here, by tracking back the arrows, I can actually find a path which gives me something like this. So here, based upon a set of weights and the algorithm itself, I was removed here, C was inserted here, and you can actually work out the way it was probably edited. This gives you many different edit sequences that are possibilities. You're using weights to say what's the cost of moving from word A to word B, so you can have these as weights. And you can end up with this probabilistic estimation of, given these different possible edit sequences, which was the most likely one to happen. The other problem we have in text retrieval is to do with very large corpuses, or corpora of documents. In the world I live in, when we're dealing with documents for life science companies, our customers may have 10 million, 50 million, 100 million documents, which are all managed in systems. So if I've got a particular document and I want to be able to go and say, are there other similar documents in my document management system? It can be quite a heavy, difficult problem to solve. Okay? Because the Levenshtein mechanism I told you will give you an edit distance, but that is hellish expensive in terms of space and time. You're not going to do it for large numbers of documents. So is there a mechanism we can use otherwise which reduces this? And this algorithm, these 2 algorithms, I just love. Computer scientists out there
hashing. We know hashing, don't we? Yeah? One of the characteristics of hashing is that if I hash two objects, the hash values I get don't reflect whether they're similar or not. Okay? They end up in buckets and they can be very different. So I can have something which is very, very close, but ends up with two hashes which are wildly different. Well, there's this technique called min-hash, which it is a hashing technique, but what I actually do is I create a number of hashes, okay, typically around 200, using a particular technique. I've given you references here if you're interested in maths behind it. But what I can do is for a document, which can consist of megabytes of information, I can come up with 200 integer hash values. And that's like a document fingerprint, okay? And you can imagine, and that's actually very, very quick to do. So you can imagine in my document management system, not only do I store the document, but I can also go and create the min-hash values for them and store it. There's very little penalty to doing that. Do you remember Jacquard's similarity? Can I tell you what the correct answer to that is? Yes, I do, because it's 5 slides back. Hands up if you remember Jacquard's similarity. Good. Okay. If we've got these 200 hash values for document A and 200 for document B, they use the same hashing mechanisms. I can use Jacquard's similarity to tell me whether those documents are similar or not. Now that's magical, because can you imagine that if I want to go, I got this candidate document, I want to go and find another document which is very similar, I don't have to go back to the original documents anymore, I can actually just look at their 200 hash values. Very, very fast, very, very quick, because Jacquard is fast. Now, you even get to a point, though, where if I'm at the 50 million document level, that still becomes too slow. So there's another technique called local sensitivity hashing, or LSH, which is not to be confused with other algorithms called LSH. But what this does is it actually takes min-hash onto another step, onto another level, at which it actually uses buckets and other techniques, I won't go into details of it, to actually categorize documents into similar clusters, and therefore I don't have to go and look across all the documents I know which candidate cluster to go and look at in the buckets and things like that. So this actually allows us to go and find documents extremely quickly in a very, very large document repository. So we won't do those today, but I've written up some of the implementations. These are actually implemented in C#, which 4 or 5 years ago I was using for this stuff. I don't use it anymore, but they're quite good algorithms. So those are text retrieval mechanisms, and whether you're in research or whether you're in commercial world, can you see how some of that stuff then starts to become relevant and useful? Because we're not really, if you go to a commercial world and you look at people dealing with documents and text, they don't really look inside those documents. They don't look at what's in them. They just treat them as a document. And now we're actually starting to introduce mechanisms which allow us to analyze those documents and find out information about them. Now, the next stage then is the natural language processing area. Okay? You all agree so far we've just been counting things. Yeah? It's all numbers. A term, word, it's just a word, we give it a number, we analyze it. So natural language processing is about trying to understand the text that we're working with. And there's many different ways in which we can understand the text. One simple way of doing it is to look at the semantics of it, the meaning of the words that we're using. And one of the problems that we have there is that words aren't static, they don't just have one meaning, they're not just used in one way. And so we end up with what's called the homonym problem, that words with the same spelling, but with different meanings, okay, can be used in different ways. Their meaning is different. And the meaning is dependent upon how they're used. Okay? And that's a very, very common problem. And can you understand, this should be fairly obvious now, all the techniques I've told you before cannot deal with homonyms. Okay? Because it's just work. So other things so that's the semantics of it. The other thing is that we want to often use part of speech tagging. And there's some very good part of speech tagging systems out there. The NLTK toolkit I've told you about already can do that. and Stanford University have probably the best system for part-of-speech tagging. And what that allows us to do is to take a statement like fruit flies like a banana, and what we can do is we can analyze that text, and we can say this is the adjective, this is a noun, so we've now got a noun phrase. This is the verb, this is the determinant, this is the noun, this is a noun phrase, determinant, noun. Here's the verb phrase because we've got the verb and the noun phrase here. Okay? So you can see from here that we've now worked out that the text is fruit flies like, and like is used as a verb, so it's I like, you like, we like, okay? And therefore it makes the statement that fruit flies are partial to eating a banana, okay? And you look at that piece of text, and that's the natural way you would actually understand that, okay? But there is ambiguity in that phrase. You look at it carefully. So we can use like as a verb. Fruit flies like to eat bananas. But we can also come up with the rather obtuse meaning of this, which is like as an adjective, that fruit flies that look like a banana. Now, those of you in zoology realize there aren't many fruit flies that look like bananas. And therefore, to our cognitive brains, we completely disregard that second meaning. Okay? It's meaningless. It doesn't make sense. But can a computer do that? The answer is no. Okay? All it can deal with is coming up with the part of speeches and then apply probabilistic techniques to it. Okay? How many times has the sentence fruit flies like a banana been used to imply if a fruit fly looks like a banana? Okay? Probably not very frequently. And so therefore that helps us with the disambiguation. And one of the things that's happened in natural language processing, this stuff's been well understood for a number of years now, but what's actually happened is we've now got sufficiently large masses of text and understand their meanings, so we can start to do disambiguation by working out the probabilities of whether this is actually going to be an adjective or a verb. So that's sort of the work that's happening on the verb. The other thing is we've also are interested in sort of the word relatedness and the concepts around the meaning of words and how they relate together. And there is a library or a database called WordNet from Princeton University. And what this does is it actually looks at most of the words in certainly the English language, and it analyzes them for whether they're used as verbs, adjectives, etc. But it also looks at the relatedness of words in such a way that, for example, if I got the word car, okay, a car can be composed of an engine, doors, tires. Okay? An engine can be composed of I'm on thing around here, carburetor, would that be about right? I presume it is, yeah. And so therefore, we can use something like WordNet when we're looking at the meaning of words to look at the relatedness of words as well. WordNet, unfortunately, is actually no longer a supported project. There's no funding left for it. And part of that reason is because we're actually moving on with these very large corpuses of data. We're not reliant on people coding the relatedness between these different objects. We can go and work it out ourselves. And that's the next thing to really look at. And that's one of the big changes that's happened around natural language processing. When I did my first course in natural language processing, which wasn't long ago, it was about 7 or 8 years ago, the Frequentist view was the way in which everything was done. Then just a couple of years ago, 2013, this next technique I'm going to talk about was developed. And it and with neural networks, almost completely blew away the Frequentist view. Now, as it happens, the Frequentist view, like all things, is still useful. It still has great value. And I think there is a tendency to say it's old, we don't use it. It has a lot of applicability. We know the difficulties of training neural networks and that type of thing. Sometimes they're just easier to use. But let me tell you about word embeddings, or word-to-vec. This is a crazy technique, and you will have heard about alchemists who turned metals into gold back in the sort of 13th century or something. And when I first read this, it felt a bit like that. So what do we do with word-to-vec? Well, this is an unsupervised semantic analysis from a corpus of terms. What do we mean by that? Well, give me 100, give me a few million words, okay, from a set of documents. Give me then the order in which they appeared in those documents. And using this technique, I can relate back to you the relatedness, the semantic relatedness of words in that corpus. Okay. Do you remember I gave you the example of the queen and the king? Frequentist has no idea that they're related. This technique will tell you they're related. That's magic, isn't it? Yeah? So what it does is, it defines a number of dimensions for the semantic space. It's an arbitrary number, but typically something like 300 is used. And the idea is we're going to create a dimensional space of about 300 dimensions, and what we want to do is we want to inject the words into that dimensional space, such that words with semantic meaning appear close together. Those words which are semantically removed are further away. Okay. So can we do that? Yes. So what we do is we take our text and we move a sliding window across it, and what we end up with is training samples. I've given you a reference here to an excellent blog. This guy actually describes this much, much better than I can do. So if you're interested in this technique, go and read this blog. This example here is the word I'm looking at. Okay. And what this does is just using, I think it's using the previous word. Yeah, it's the previous word it's using here. Sometimes the windows can be quite big. The sliding window can be 2 or 3 words before and after. What that does is it generates a training sample. And then what we do is we actually create a neural network. And our neural network has these input vectors of the data I've just explained. There's a hidden layer, which if you remember from previous meetups, these have a set of learnable parameters associated with them. And then we have the output layer, which is a softmax classifier. In this technique, we actually ignore entirely the output layer. All we use it for is just to do the loss function. Remember the loss function? All we want to do is to minimize the loss function. And the loss function, simply put, is the loss function is organize the positioning of the words such that their relatedness is dependent upon the way the words are used. So, for example, another example might be the dog sat on the mat. Okay, the cat sat on the mat. Those 2 words are actually used in the same way, aren't they? And therefore, we assume there to be a semantic relatedness between dog and cat. That's how it actually works. Okay. So, do you remember I told you about a word is known by the company it keeps? Yeah? This is how we work out the semantic relatedness of these words. So the loss function here is about training a set of parameters here. These parameters in hidden layer is the weight matrix. I've assumed here that I've got 10,000 words, and I've got 300 neurons. Why have I got 300 neurons? Because that's my dimensionality, that's the size of my dimensions. Okay. And here's my word lookup vector table. That is actually my hidden layer. So after training this and minimizing my loss function, this hidden layer here contains a set of weights for any of these particular words. These weights allow me to map each individual word into this new space, and the mapping will put semantically similar words together in the same space. And it is a bit of magic, but it's also an interesting use of the neural network, because really, I'm actually just interested in this hidden layer. The rest of it I just discard and I'm not interested in. So what do we get out of this? Well, another favourite algorithm of mine is principal component analysis, which was again what I did in college all those years back. What this allows me to do is to take my 300 dimensions and to compress it down and to try and represent that with the minimum loss of variation of the data into 2 dimensions. And so out of our word to vec, what we can actually do is we can show a mapping of our words. And I've just picked out one area here, and you can see we've got pork, veal, beef, chicken, roast, and gravy. And so out of this particular set of documents, words, I think there's about 1.7 million words in this, and it's a very disparate set of text. it's given us this relatedness here. That's the magic behind word2vec. Now, how can it be used? Well, imagine a situation where you have a search engine, okay, and I type in I like beef, or search for beef or whatever. You can actually use the semantic relatedness of this, which is learned from the documents in the corpus, to know that perhaps I might actually also return veal and pork, and perhaps a touch of gravy with it as well. Because we have that in our model, very simple model of the relatedness of these words. Now, when you actually look at one of these, you realise that actually, some of it is just a bit noisy. You start to, particularly in the middle, you start to look at stuff here, and you're looking at some of the words. You won't be able to read them from back where you are, but hot, any, than, should, some of those feel relatedness. Do you remember we talked about the problem of homonyms, of words which they're spelled the same, but they have different meanings? Well, this system can't work it out, can it really? Because it's still dealing with words. And the fact that word might have two semantic meanings depending upon how it's used. You've almost got like a tug of war. Some sentences are pushing the word over there, and other sentences are pushing it down here, and it ends up in the middle. Can we sort that out? Yes, there are techniques for doing that. Okay. And part of it involves looking at sort of the part of speech type analysis to say how is the word actually used. Because then, if I got a word, which is there and there, for example, which are two different words. That's not a good example. Anyway, what you can actually do is you can actually substitute. You can have word 1 and word 2 as being the two different variations on those two words, and therefore they get injected into the space. So there's a lot you can actually do around this. So that's word2vec. There's actually a version called doc2vec. Yeah.
Can I ask a question?
Yeah, I'm sorry. Yeah, of course you can.
So what happens when two words are the same but mean different things in different contexts, where they're actually the same word? So beef, for example, there's a cluster of words to do with farming, and there's a cluster of words to do with eating.
Yeah.
It's the same word, they mean the same thing, but in each cluster.
Yeah. So that's very much it's the same concept, but yeah, it's used in two completely different ways. It will end up in the middle. Unless you can do something in addition to do some preparation for that word to say that there are two different contexts in which it can actually be used. Because I think the important thing is to remember is the word can only appear once unless you actually inject it in as two different words. So you might have beef farming and you might have beef eating or something. Yeah. Anyway, there's a lot of merit in looking at that, and I think the magic of it is that we can actually get semantic interpretations and relatedness of these words. It's a great question, Bob. Now, here's a bit of fun. I can't remember, I wasn't here on the first meetup, but did you come across recurrent neural networks, RNNs? Okay. RNNs are one particular type of neural network which have the ability to do local, they actually learn, they have state, I can describe it like that. So normally when you train a neural network, there's no state being managed in the neurons as they're being learned. This actually allows you to manage state. And it also has the advantage that you can actually put variable lengths of text into an RNN and have it trained for the text and do stuff with it. I'm not going to go into this in detail, but RNNs are the type of neural network which are most commonly used with text analytics and natural language processing. I mention this because there's this blog which makes me laugh every time I look at it. It's the unreasonable effectiveness of recurrent neural networks. Okay? And this guy, what he did was he said, find me some corpuses of different types of data and let me create an RNN and use it as a generative model. Now, the idea of a generative model, and they're frequently used in text processing and in analytics, the idea of a generative model is, you give me a word, and I tell you what the next most likely word is. Okay? And then I take that word, and I put it into the model, and I get the most next likely word out of it. Okay? And it's called a generative model, because based upon a set of learnings or a set of probabilities or whatever, you can actually go ahead and generate new text. Sounds a bit crazy, doesn't it? So this guy, he obviously had too much time on his hands. He actually, the first thing he did was, and this has been commonly done, is he took the words of Shakespeare and trained an RNN on it, and then he could start to generate text that looked pretty much like Shakespeare. Of course, there was no plot or whatever. But anyway, then he looked at other things. And the one I really liked is he took the Unix or the Linux kernel and in fact a whole bunch of other source codes. And what he did was he trained a generative model using an RNA on the C code that forms Linux. And then what he did was he said, let me see if I can generate some code. And here's an example. I don't know if you can see it at the back. Any of you C programmers? Yeah. Hey, Peter, come up here. Tell me what this piece of C code is doing.
A second.
Yeah, that's okay. Well, actually, first of all, does it look like C code? Remember, this was actually created with a neural network. Okay? No one wrote this code. What do we start off with?
So, okay, function note returns nothing, takes us s.info, pointed to an s.info struct. Okay.
Do you think it would compile?
now you're asking. Okay, my answer is yes, I think it will compile. It looks like it's got all the semicolons in the right place.
It has. The RNN, just from this large corpus of C code, has actually learned the C programming language, the syntax and structure of the C programming language. So it's learned, for example, that typically you put comments at the beginning of it. If any of you are programmers, you know that's not the case. Static void, function name, open bracket. Here we have a struct as a pointer to a struct, close bracket. It knows to match brackets. And there's examples here, for example, of open bracket, unsigned long. It knows how to cast, and it knows how to close. It also knows about the opening braces. Notice it doesn't get into the argument of where you put the opening braces and close braces. Okay, that's something which we don't worry about. But it's quite remarkable that it's actually learned how to do that. And this guy, have a look at it. It will make you laugh. Any of you use LaTeX in terms of yeah? He trained it on a bunch of LaTeX and he started writing reports using LaTeX. I don't know whether he actually tried to publish any of the papers he produced, but you never know, it could happen. Anyway, that's a bit of fun, but do have a look at that. And that shows us some of the ways in which machine learning is working with natural language processing. Some resources and references. Throughout these slides, you'll find that there's references to better explanations or more full explanations. If you're interested in learning about natural language processing with deep learning, on YouTube there is a course from Stanford. It's actually one of their master's courses. And it's a guy called Christopher Manning and a couple of others. And it goes through how to actually create word-to-vec using the neural networks. It uses TensorFlow. It has an exercise on learning TensorFlow. It also talks about some variations on word-to-vec, like doc-to-vec and glove. But that's very, very worth a look. And also, if any of you are trying to tackle the understanding of neural networks and their learning and backpropagation, there's actually a whole lecture on there which actually explains it in ways you can almost understand. It's remarkable. If you're interested in machine learning in a more general way, this book here by Aurélien Guérin, Hands-on Machine Learning with SciKitlearn and TensorFlow, is the best book I've ever seen. It is absolutely brilliant. He actually goes in, there's two sections on it. One is SciKitlearn, which is traditional machine learning, and then there's a whole section on TensorFlow, and he talks about RNNs and using it for text analysis and everything. It's a really, really good book. Also, the notebooks are available here. He's got some Jupyter notebooks, which actually go through all of the examples and more. We will obviously make these slides available to you, and so therefore don't worry about having to write them all down. If you want to go to understand natural language processing in its essence, then this is a really good book. This one here
which is speech and language processing by Daniel Jurafsky and James Martin. And that really goes into the whole linguistic approach, if you want to know about parts of speech and verbs and adverbs and this type of thing. And also, how is speech recognition done? Because that's not only understanding the fact that, you know, there's wave signs and that type of thing, but how do you break them up into words and how do you recognize? It goes into that in great detail. And then lastly, if you want to know more about the sort of frequentist view of the term frequencies, the TF, IDF, and that type of thing, this book here by Christopher Manning, same guy here, is really good as well. Obviously, this book doesn't cover a lot of the stuff in here because it's from 2008, but that goes into probabilistic models for text retrieval, etc. And it also shows you how you can actually go and build an index set of documents if you chose to. So hopefully that's my introduction to text retrieval and natural language processing. I hope it's given you some ideas as to the types of things that people are doing and the types of algorithms which are there.